If you think of an object instead of as a giant mass, but a whole bunch of little masses, they're still all falling at the same rate. And we are, of course, ignoring air resistance. Oh, that's right, back to that problem. So once you can think through that the acceleration is the same for all of them, and we are talking vector acceleration. So if I have something that's going, mass is irrelevant, if I have something going up into the air at 15 meters per second, and I'm on some strange planet where the acceleration due to gravity is 10 meters per second squared. Well, so what's the direction? If we're talking about the vector, what is the direction of the acceleration?
Down.
Acceleration due to gravity is always down. Down is defined as the direction of acceleration due to gravity, or the direction of the force. When I let go of this, down is defined. So if we make up positive, my acceleration is negative 10 meters per second squared. Which says that, well, that's the same as negative 10 meters per second. Mathematically, those are equivalent. And that's my change in velocity over time. So for every second that passes, my velocity changes by negative 10. So I go from positive 15, and then I subtract 10, I get 5 after 1 second. I subtract 10, and I'm going negative 5 after 2 seconds. Subtract 10, I'm going negative 15 after 3 seconds. After each second that passes, I'm losing 10 meters per second, or if we're talking about Earth average, I'll lose 9.8 meters per second every second. And Mars 3.7 meters per second every second.
On the quiz, you want us to measure acceleration due to gravity as 9.8 or negative 9.8 or negative 10?
The negative depends on which way. Negative assumes down is negative.
Yeah.
9.8 or 10, either one.
Okay.
I mean, on this quiz, the answers are close enough that I don't think someone's going to take a wild guess and just happen to fall in that tiny little range between the two.
Okay.
So therefore, if all I'm going to do, if I assume up is positive, all I'm going to do is subtract 10 every single time. The first one started out at 10 meters per second. Positive, I'm going to still make up positive. The other one was 15. And then I think it was 3 meters per second. That's where I start, and then I subtract 10 every time. So that would be 0, that's hitting the peak. This one's at 5 meters per second. It's still positive, so it's still going up. And this one has already hit that peak, and it's coming back down. And so I think part A was to rank their speeds. So those are the velocities, speeds, we just look at the absolute value. So 0, 5, and 7. So this is obviously the fastest after 1 second, next fastest, and the least fastest, slowest.
Cool. Sounds good.
Bailey, was that, I think you were the one asking this, or Brianna, sorry. Was that
Yes.
good enough?
to go.
I have
Yes,
a
Hope.
question to just go back to the acceleration due to gravity. You want us to write it differently on our forces when we're doing our forces, or when does this apply when you want us to write acceleration due to gravity?
When you're doing force diagrams?
Yeah.
You
'Cause
would
I'm
not, if you're doing a force diagram, you do not write the acceleration due to gravity at all.
Okay, so do you want us to write weight
At
for
this
gravity?
point, I don't think there's anything that we've dealt with now where weight would not be appropriate for the force due to gravity.
Okay.
It's not till we get to chapter 9 that we would need the more general version, which is just F with a lowercase g.
Right, okay, thank you.
And that, chapter 9 is when we start getting into sort of planetary motion, and there's a gravitational pull between the Earth and the Sun, but it's not close enough to the sun to call that force weight.
Thank you. I'm not-
Other questions right now? Okay. Are we, then, I guess, ready?
No, can we have 2 minutes, please?
You said 2 minutes?
Yeah, can I get just 2 minutes to look over everything?
Sure, as soon as the last question's asked, we'll go for it.
Okay.
I have no problem with that. Jasmira?
I have a question, but it's not about the work that was in the book. It's about, I had emailed you about, I was struggling with with 14 on the,
Oh,
yeah.
that's right. I did see that. I apologize for not responding. I forget what number 14 is. Ah, okay, this is wrong, man, part of that? So some of this relates to the stuff that you're doing in the lab on Tuesday. This does not relate directly to the chapter 3 material. Sorry, that was badly worded. To the homework problems from the textbook and the quiz. Is it gonna mess you up if I talk about this now?
Yes.
Yes.
Okay,
I mean, are you taking points on the master set if it's wrong?
you are supposed to be doing the master set to get correct answers.
Oh.
Here's what I'm gonna propose. Let's give the 2 minutes, do the quiz. Right after the quiz, first thing I do is this. All right,
I had a question.
oh, yes.
about, 46.
46,
41.
the boats. Okay, so in 46, we're talking about the boats going across the river. And so we have two different velocities involved here. We have the velocity of the rower, and then we have the velocity of the river. Badly worded, we have the velocity of the rower with respect to the river, then the velocity of the river. So for instance, in A, he's paddling upstream, and the river's going that way. So the net result of how fast he is going, or sorry, the net result of his velocity is the sum of these two vectors. Because everyone loves the shorthand notation in the alphabet soup of physics, this would be the velocity of, we'll just say the boat with respect to the river, and this is the velocity of the river with respect to the ground. So if you want to know how fast the boat is going with respect to the ground, well, you add the two. So, well, adding vectors, something like that. And so this would be the resultant. This is his velocity of the boat with respect to the ground. In other words, if you had a radar sitting on the bank and you had a radar gun, that's what you detect, assuming you were straight in front of him. B, he's going straight across. He's trying to go straight across, so he's rowing in this direction, but the river's dragging him down that way. So the net result would be that way. So we're just basically probably stick some color here. Adding the two vectors again. And then the last one, he's rowing partly in the direction of the river. The river's going down. And again, we're just adding the two. Similar to the stump problem in chapter 2. Now, so the time to, so the fastest ride, let's do part B first. The fastest ride would relate to the longest arrow. From a conceptual point of view, if I'm rowing partly with the river, I'm gonna be going faster. So that's gonna be the fastest, the next fastest, and then when I'm fighting against the river, the least fastest. Or, as we discovered earlier, slowest. Now, the time to reach the opposite side depends upon how much of the velocity is directly towards the other side. What is this component right here? And for that, he conveniently put lines in the river. Because we need to be able to look to see which of the arrows points farthest to the right. And to me, that B is the one farthest to the right, A is the next farthest to the right, and then C is the next farthest to the right. So that would be the order in which how fast he's actually crossing the river. But then Hewitt decided to not ask about who's the fastest to the other side, but the time. So the faster the time, the faster the speed across the river, the less time. And so the answer to part A would be the reverse of what I just did. C is going the slowest, so it has the most time, then A, then B. If you did not have the lines on the river there, it'd be a much tougher one to answer. There's another one in chapter, I think it's chapter 10, where you also have to basically define the way he's drawn it. Bill Hodge, does that answer your question? Okay, other questions right now? All right, in 2 minutes, I'll hang up for this. Guess we don't need to record the silence for 2 minutes.